Okay.
Looking forward to it.
I see a lot of familiar faces here, so that's great. Obviously, the Mahomet Aquifer has a lot of local interest, and so I hope to answer some questions. I think there's a lot of people here that know more, as much or more than I do about the aquifer. So when the tough questions come, I'll refer to them. But we're gonna talk a little bit about sustainability. We're gonna talk a little bit about groundwater law. We're gonna talk more about some basic groundwater stuff, because I know a lot of you here aren't groundwater engineers at all. So I think we all need to have at least some common footing to start from. Okay, and once I figure out, okay, now it's going to go past. Okay. Before I get started, though, I would like to acknowledge the help of several people. Ed Maynard over at the Geological Survey. He and I and Derek Winstonley have put together some presentations in the past, so I'm borrowing slides from all of them. And as well as some modeling slides, George is our resident modeler. We'll talk about that a little bit towards the end of the presentation. George, wave your hand. Any modeling questions? I'm going to go to George, okay? So here's the Mahomet, and we're going to discuss a little bit about how this was formed and what it is, but before I go too far into the talk, I thought I at least should show you a picture of, or a map of where the Mahomet sits. And so you can see that it comes into Illinois over here on the state line, up by Hoopeston, and kind of meanders across east central Illinois and ends over at the Illinois River. So it's a pretty big system, and a lot of towns, a lot of people depend on it for water. About somewhere on the order of 70 million gallons a day is removed just by municipal users. Now, as I'll discuss in a little bit, over here in Mason and Tazewell County, very large irrigation area, and in the summer, during the irrigation season, they're probably pumping on the order of 300 million gallons a day. So a lot of water is annually pumped out of this aquifer system. When we talk about sustainability, and that's what this whole seminar series is about, there's a variety of definitions, and you can all come up with your own. This is one that is commonly seen, the ability to meet the needs of the current generations without compromising the ability of future generations to meet their needs. One of the questions that comes up with a definition like this is, what are those needs going to be, and how do we know, what are those needs beyond just basic needs? So there becomes some value-laden implications in some of these terms, especially this term used by the U.S. Geological Survey. In fact, I brought along a copy just to show you this publication, Sustainability of Groundwater Resources. You can get it online. It's really a very good document for just some basic general concepts regarding groundwater, surface water interactions, and sustainability issues. I recommend it as something to read. And you don't have to be a PhD to understand it. It's written for the level of common understanding. But in this definition, we talk about development of groundwater in a manner that can be maintained without causing unacceptable consequences. And it's that unacceptable term that's really the catch-all. Who defines what is acceptable and what is not acceptable? As an engineer, especially as somebody working at the state survey, we really can't make those value judgments. We can discuss what impacts of development will be, but it's really up to the decision makers, the city planners, what have you, to say this is an acceptable impact or not. And we can at least try and describe what those impacts will be and let them understand what the implications of that are. So that's kind of my soapbox for sustainability at this point. Let's talk a little bit more about water. I commonly start off with this slide just to show the interrelationship of all aspects of the water cycle, from precipitation, surface water runoff, groundwater. And the one thing that I want to try and emphasize through this is that they all are linked, and especially when we start talking about groundwater, we have to understand that the common or natural discharge point for groundwater is surface water. And so if we develop groundwater, we're going to impact the amount of water that might be available in surface water. Now, there's some interesting relationships. For example, here in Champaign, when we pump water out of the Mahomet, that goes through our distribution system here and out one of two wastewater treatment plants, either the one over in Urbana that goes down to the Vermilion and out to the Wabash, or the other one goes out the Kaskaskia ditch and down south. Neither one of those river systems are really interrelated to the Mahomet Aquifer at all. So we're taking water out of the system and not putting it back into this system anyway. Now, the other thing I want to make sure that we go out of here understanding is that the aquifer, the Mahomet Aquifer, it's a sand and gravel body. It's not a hollow space underground. And so the water is actually occupying the pore space of the sand and gravel. There's a lot of misconceptions that this is an underground river. It was formed by a river valley, and I'll talk about that a little bit more, but it's filled in with sand and gravel. So you can stand on it, and if we went west of town, we would be. And if you're out in Mason County, you would be actually standing right on top of the aquifer. But just so we understand, this is not a hollow space underground that's flowing with water like a river. And then some simple definitions. When we talk about an aquifer, we're talking about a geologic formation that can yield water at a sufficient quantity to be economically developable. Now, that means different things to different people. What I might need for a house well is much different than what an industry might need. So an aquifer can be different things to different people. But it has to be able to provide water, at least at some sustainable amount. Now, an aquitard, this is usually an overlying layer that impedes the movement of water into the aquifer. These tend to be fine-grained deposits, clay and silt and what have you. And around here especially, these tend to be confining layers, and I'll talk about that in a second. So we talk about unconfined and confined. Now, unconfined aquifer is one that's basically in communication with the atmosphere. These tend to be relatively shallow for the most part, versus a confined aquifer, which is underlying this confining bed that I mentioned before, and the water in there is under pressure. Sometimes these are called Artesian aquifers. And what's interesting about the Mahomet Aquifer is it's both. Here in Champaign County, in the eastern end of the aquifer, it's confined. As we get out to the west in Mason and Tazewell, it's unconfined. And there are some very big differences between those two conditions. And I'll discuss that in a minute. So here's a picture of an unconfined aquifer. And here we've got land surface, and there's some zone here that's unsaturated. In other words, the pore spaces contain water but also gases. At some point, though, you get down to a level where all the pore space is saturated, and the top of that saturated zone is called the water table. I think most of us are familiar with the water table because that's the water that gets in your basement. Okay, so especially around here, the water table is pretty shallow. In the springtime, it's probably within a few feet of land surface. And in order, of course, for our basements to stay dry, a basement's usually going to be constructed down into the water table at some points. And so in order to keep that basement structure dry, you've got to pump that water out of there. So some pumps are what we use. Now, a confined aquifer is underneath some type of confining bed, or in this case, some clay, fine-grained material that impedes the movement of water downward into it. But when you're down in this aquifer, if you were to drill a well into it, the water pressure is enough to push the water level above the top of the aquifer. So here's the top of the aquifer, and the water pressure is pushing the water level up to this height. Okay? Now, one way to think about this is it's analogous to our plumbing system in our home. We have pipes in our home. They're filled with water, and you keep the faucet closed. There's pressure behind that. When you open the water faucet, though, the pressure is released. And this is very much the same. The pressure is released here when we drill a well into that system. Now, one could ask, well, how is the pressure applied to that? Well, typically, that's coming from some distant area where there's water recharging the system and putting a head on the aquifer, putting some weight or head. You also have the weight of the materials overlying the aquifer also putting pressure. Now, the main thing to remember, though, is that everything below the water table is saturated. So all that pore space is saturated from the water table down. Now, here's a quick little depiction of an artesian aquifer. And hopefully it's going to go. Okay. And there's the water level. And in this case, the water level in the aquifer is above the water table. And in some cases, and we see this in the Mahomet in some areas, especially as we go north up into Ford and Iroquois counties, there's enough pressure on the system to actually cause wells to flow. There's nothing really mysterious about that. It's just there's enough pressure to push the water level above land surface. And there are a lot of flowing wells up there. A lot of them are basically not capped, and so they flow all the time. So they're continuously releasing pressure from the aquifer. I'm not going to make a value judgment on that, but one could argue that that's a waste of water. And one of the things that, in fact, I'm going up to Watseka tomorrow to talk to them about an ethanol plant that's being proposed up there. They want to know what the impacts of that will be. I think one of the impacts will be is that a lot of those wells will stop flowing. That may cause concern with some of those people because they use that water to feed a pond or something like that. Well, they may have to put a pump in that to get the water instead of just letting it flow. Okay, now I mentioned this groundwater surface water impact, so I'm going to show you a really simple demonstration. This is my desktop model of an aquifer, and what we have is a constant head source of water over on this side, a constant water source over on this side, and a stream in the middle. And we're going to inject dye into this system from the edges. And you'll see as this progresses how the water moves to the stream. And the main thing I want to point out here is how we get this vertical movement from deep up into the stream from below. And this can occur at scales of feet to miles. And especially when we start talking about the Mahomet Aquifer system, we're talking about several hundred feet vertical and literally, dozens of miles in the horizontal direction. The aquifer is feeding in part the Vermilion River, the Sangamon River, and certainly discharging at its ultimate discharge point down at the Illinois River. So, there's this natural system is occurring all along the aquifer. And now let's get into a little geology, and please bear with me, those geologists in the room. But here's a bedrock topography of a bedrock topography map of kind of Illinois and Indiana. And the high spots on the bedrock surface are these green areas, like up here around Galena and down in southern Indiana. And the low spots are these pinker areas throughout here. And I think you can readily see some of the current modern river valleys. For example, the Wabash River Valley, the Illinois River Valley, the outlet for the rock anyway. What's interesting, of course, this is the ancient Mississippi River Valley through here. The Illinois River happens to occupy that position for a good portion of it. But when the glaciers came, they basically pushed the Mississippi over to its current location on the edge of Illinois. So that's a remnant of some pre-glacial work. Now, the one thing, of course, that we don't see imprinted on the current land surface is this bedrock valley right through here. It's the buried valley. That is the Mahomet Bedrock Valley. Now, another thing you'll notice here, and some people have pointed this out before, is this kind of valley going back off this way. And people have called this the Mahomet Tays, T-E-A-Y-S Valley. And there has been some trace of this purportedly across Ohio and back up into West Virginia. That is an ancient pre-glacial drainage valley. But as in terms of being an aquifer, it's not really the case. Once you go east of Illinois, probably as far as Lafayette, that's about the end of the usable part of the Mahomet. As we go farther east, that valley tends to be more filled with clay than sand, and so it's not really much of an aquifer. And the idea that water's moving down that valley and recharging this aquifer from West Virginia, let's take that out of your mind right now. That doesn't occur. Okay. However, we do see, and I will show you, there is movement of water down the valley. So here's another picture of the Mahomet. You've seen this before. Just to kind of put you in current context. Now, one of the things that I added to this map, you see all those red stars. That's where ethanol plants have been proposed across the aquifer from Watseka to Havana. None of those have been built yet. There's a lot of question as to whether any of them will be built, but they're all seeking permits or have been granted air permits anyway. We'll talk a little bit more about groundwater law at the end of this discussion as well. But that at least kind of gives you an idea of where we sit, where the aquifer is. Okay, a little bit more geology. This is a quaternary map of Illinois. So this is showing the glacial deposits on the surface. Okay, and the main thing I want to point out here is the last glaciation left a series of moraines and glacial deposits on top of the Mahomet. But one area that it didn't get to is over here in the Mason Tazewell County area. So that will become important for them. The area around here is buried by these glacial deposits. As we get over to the west, it's not. So we have this confined aquifer over here, unconfined over there. A little bit more glacial process. We're talking about massive amounts of ice carrying a lot of debris. As that water as the ice melts, and we're talking about water flowing off that ice, it's transporting a variety of materials from clay-sized particles to sand and gravel and boulder-sized materials. And as you know, the heavier particles, the sands and gravels, and the larger sized materials, they're going to be the things that settle out of that flowing water most rapidly. And so what happens is that sand and gravel tends to fill up the bottom of the valley. And so you get the bottom of the valley filling in with sand. And then over the top of that, you're going to get the finer grained materials, the silts and the clays that lay on top. And as we get various geologic episodes that progress across the landscape, we see succeeding materials on top that can also vary. Now, we have the Mahomet Aquifer, the sand, filling up the bottom of the valley. Then over top of that, we'll have a deposit of clay materials. Then on top of that, we may have another series or sequence of sand and gravel, and then more clay, etc., until we get up to the land surface. Now, here's a kind of a depiction. This olive color here would be the Mahomet, and we have this bedrock high sitting in here, so the sand and gravel's gone around that edge. And then we also have, various clay deposits sitting on top, and then other sand and gravel units laying above the Mahomet. Now, what we're finding that is most important is that where these sand and gravel deposits lie over the Mahomet and are connected to the Mahomet will really dictate where a lot of recharge will occur. Recharge is occurring from land surface, rainfall and snow melt over the aquifer, penetrating the ground, moving vertically downward. The aquifer is not being recharged from Lake Superior or Lake Michigan or West Virginia or Ohio. It's coming from the rainfall we get right here in Illinois. Here's another picture. This is a picture from George's model. And what we've done is taken a slice down the length of the valley. And what you see, what I really want to show here is here's the Mahomet Aquifer laying in the bottom. And you can see the overlying material sitting up here. And the way this vertical exaggeration is makes it look like Illinois is really mountainous, but it's not, of course. But what you see clearly, I think, is that over in the eastern end and over this way, we have quite a bit of material sitting on top of the aquifer. And then as we get out here over towards Mason and Tazewell County, that overburden is gone. Here's the Illinois River Valley coming down through here. The other thing that I'll touch on a little bit, too, is that in the model, we have a pretty good depiction of the geology of the overlying materials because of work that's been funded by various groups in that part of the aquifer system, Bloomington Normal and the water authorities in that area. As we get back over towards Champaign County, we don't have that detail in the model. And that's something that we're currently working on, is better defining the geology so we can add that detail to the layering above the Mahomet. And that's going to have a lot of influence on that recharge factor in the model. So here's the the major sand and gravel aquifer map for Illinois, and you can clearly see then the Mahomet Aquifer sitting in here. What's important, I think, is also to look at the amount of water that's being used. And this is a compilation of water withdrawals from the aquifer lumped on a township basis. So each one of those squares is a 6 by 6 mile square, township, 36 square mile. And you can see when we look at the Mahomet, where most of the water is being withdrawn, and it's right here, as well as, now this happened to be, interestingly enough, we compiled this information, I think, from 2000 pumpage. And it just so happened that that was the year that Decatur used their well field, and we'll talk about that a little bit. Decatur has an emergency well field that they can pump water out of the Mahomet into the Sangamon River, which then replenishes their reservoir. So at certain times, certain drought periods, they need to turn those wells on. They can actually then use Mahomet Aquifer to replenish their lake. You can also see up here Peoria, Pekin area. Those are the main features I wanted to show on this map. And I just compiled some pumpage data from local communities. And obviously, the big water user is us. We buy our water from Illinois American at the rate of about 23 million gallons a day. Decatur, when they are pumping, they might remove somewhere on the order of 12 million gallons a day, but it's short term, maybe 2 or 3 months. Now, they did operate this past fall for a couple months, but that's not a constant 365 usage. That just kind of gives you some perspective as to who's using the water in this area and who the big gorilla is, and that's us. Now, how do we get water out of the ground? I'll talk a little bit about well hydraulics, and then we'll get into sustainability. Put a well in. A well is really just a structure in the ground that keeps the sand and gravel from collapsing in the hole. So at the bottom of the well, there's what we call a well screen, or it's basically a casing that's got holes in it that allows the water to come through, but yet keeps the sand back. And you put a pump in there. The pump discharges water to the surface. So the first thing that happens when you turn the pump on is it pulls the water out of the well casing. That immediately causes a head difference or a water level difference between the water level in the well and in the aquifer outside of it. And as we all know, water wants to seek its own level, so water starts moving to the well to try and negate that head difference. And over time, what develops is this cone of depression, or this different water level surface that we see like here. And if we look at that vertically, these circles then depict the water surface topography. And just like surface water, groundwater moves downhill, and so it's going to move perpendicular to those contours. So we have a radial pattern then of movement to this point right here. So water's moving everywhere radially towards that discharge point. Does that make sense so far? Okay. Now, what happens when we add more than one well? And we'll go back to the desktop model again. Here we have a situation where we've got a bunch of small wells or piezometers that we're going to use to measure the water level in this aquifer. And we're going to turn one of these wells on and pump water. And that yellow line there is actually drawn on the map. What you can't see from the back of the room, I'm sure, are the little wax rings that depict the water surface and all these little piezometers. But that yellow line there depicts that cone of depression in this aquifer system. Now, it's not that nice, perfect picture that I showed you before, because the edge of the aquifer over here is impeding the flow of water to this well. We have a nice constant water source over here, so that just heads right to that surface. Okay, now let's turn off well A and we'll turn on well B. And we're going to get a different cone of depression. Now what happens when we pump both together, we get this red line at the bottom. And that red line is the simple addition, mathematical summation of the drawdowns created by each well individually. And we could add a third well, a fourth well, a fifth well, and all those drawdowns are going to be additive. And that's basically what our models do, is they can determine what the drawdowns will be and then add them together. The trick is determining what the drawdowns will be, because you have to know a lot about the aquifer itself, how it's being recharged, the hydraulic properties of the system, where the edge of the aquifer occurs, all those kinds of things. And this nice ideal system, maybe that sand and gravel is pretty uniform, buried out there under a couple hundred feet of ground, we can't tell what the uniformity or non-uniformity of those aquifer materials are. So how do we do that? Well, we've got to go out and do a lot of drilling. We may do a lot of geophysics to try and examine what's buried from land surface. There's a variety of techniques, but all of them tend to be very intensive and expensive. So here now is kind of that looking down kind of profile. You can see this kind of double ring configuration from this two-well system. Now, here is a map of the water levels in the aquifer from stem to stern, from Indiana to the Illinois River. And what we have then is a potentiometric, or actually a topographic map of the water surface in the aquifer. Now, how is this made? Well, we go out to a well that's completed in the aquifer. If we know what the elevation is at the top of the well that we're measuring the water level from, and then we subtract off the depth to water, that water level in the well, then we'll get an elevation of the water surface in the well. And then we have elevations of water surfaces in all the wells that we measured, and we're literally talking about hundreds of wells here. And then we can contour that surface. And, like I mentioned before, groundwater is moving from high head to low head, so it's going to move perpendicular to these contours. And so what we see, for example, is kind of a high spot up around Paxton, and movement not only south down the valley, but we see movement up north towards the Iroquois River Basin, as well as out the Wabash Basin. But the predominant flow is down the valley. Now, what happens here? Well, we're pumping 23 million gallons a day on an average day. And so the well field out west of town has created a pretty large cone of depression to capture the amount of water that's being pumped. And what it's doing then is basically cutting off any further flow to the west. And in fact, we're pulling water back from the west to the east. So we've in a sense created a groundwater divide here by our pumping. I'm not trying to pass a value judgment as to whether or not that's good or bad. Certainly, we're depending on it, so I'm not going to say that that's a bad thing at all. Now, here is a hydrograph of a well. This is a measurement of water levels in a well over time This well is out not too far from the Illinois River in Mason County. Water table situation, and the depth of water here you can see is on the order of about 30 to 40 feet. We've been measuring water levels in this well since the 1950s, at least on a monthly basis. In fact, we have a recorder chart that we change every month on this well. So we have, in a sense, a continuous record of water levels in this well for over 50 years. And I think it's pretty clear. You can see the impact of the late 80s drought, and you can see the impact of the flood of 93. And 2005 was a pretty dry year, and it's impacted the water level there also. What's interesting is that in this area there have been 2,000 irrigation systems added to the system in that span of time. Pumping, what I mentioned before, during the summer, 300 million gallons a day. We really see no impact on the aquifer from that pumpage. Why? It's unconfined, and whatever rainfall falls pretty much soaks into the ground. It's sand at the land surface, and it just penetrates. There virtually is no surface drainage in Mason County. What drainage they have largely is man-made. And if you've ever seen one of our water survey drainage maps, you look at Mason County sometimes. There are no surface streams. There's about 2 across that whole county area. Why? Because the water is just soaking right in. We estimate recharge to the aquifer in this area is on the order of 18 inches per year. Okay? When rainfall is about 36 inches per year, half of that is recharge. That's a tremendous amount of recharge. I'm going to contrast that now with what happens over here in Champaign County. And let's just take a look at that. First of all, here's kind of where our wells are, predominantly west of town. Champaign-Urbana itself does not sit over the aquifer. Now I've also added some diamonds here. This one is the proposed ethanol plant for the Andersons. And then these other 4 diamonds represent the wells currently owned by Lyondell, a firm down in Tuscola, chemical firm. They occasionally use those wells to, basically help their wastewater effluent meet water quality standards. And so they'll pump water out of the Mahomet Aquifer down the Kaskaskia ditch to Tuscola. Well, enough said about that. There is a use of the aquifer that's literally, many miles away. I guess one good thing, perhaps, is that as we grow and use more water, we're going to be putting more water out of our wastewater treatment plant, and that water goes down the Kaskaskia ditch, so that will require less need for Mahomet Aquifer water by that chemical plant down there. So here again is this kind of a blow up of the area around here, and you can see this cone of depression that's created in the aquifer locally. All those red dots represent measuring points that we've collected data from existing wells. And here's a hydrograph of a well that we've, again, been measuring since the 1950s. This one happens to be located on Rising Road off of Route 10, north of Route 10, Springfield Avenue. And this hydrograph has been used and misused by a lot of people especially over the last, say, several years. Because people will point to this and say we're draining the aquifer. But I want to say, first of all, remember this is a confined system. So what we're measuring here is pressure. And the actual top of the aquifer is somewhere down around 550 or 530 feet elevation. So it's down here off the bottom of the graph. So what we're seeing is a removal of that pressure head off this confined system. Now, the key to that is this. Here's the growth and pumpage from the aquifer over time that's causing that head decline. If we were to stop for a moment and not keep adding or pumping more water, that cone of depression would stabilize. It wouldn't keep dropping like it is. So if we had stopped back in, say, 1970 or so back here and pumped at 12 million gallons a day, that cone of depression would have stabilized at some higher elevation than what it is today. Another way of looking at that is this, where I've plotted now the withdrawals versus the head. And you can see this straight line relationship. That's a good thing, because basically what it's saying is the aquifer is meeting the demand. If that straight line were suddenly start going off straight and start dropping more rapidly, then we would say recharge is not meeting discharge or pumpage. Now, the key question when it comes to sustainability is how long can we stay on that curve? Will we drop off that curve before we hit the top of the aquifer or not? Now, one management strategy is to say that we don't want to start pumping water levels down below the top of the aquifer. But we could, and it wouldn't necessarily be a disaster. Because what's going to happen is as the water levels fall down into the aquifer, that aquifer is going to change from a confined system to a water table system. Now, it's not going to increase the recharge rate necessarily like what we see out in Mason County, but what happens is now we're starting to dewater that pore space, and we get much more water out of storage for loss of head in a system like that. But I think as a general management strategy, we typically want to keep that aquifer confined, and we kind of draw the line at the top of the aquifer. So, will we stay on this line for that additional pumpage? That's the big question. Now, I think most of us are aware of the fact that Illinois American has proposed an additional well field west of town. And it'll be out northwest of Bonneville. And what they're proposing to do, well, let me go back, is put in a series of wells out here and then use the wells that are over here less. So they're going to shift that pumping center to the west. That's a good thing because, one, they're getting farther off the edge of the aquifer, and two, by spacing that pumpage out over a greater area, that interference between wells will be reduced. So the removal of water should be more efficient. Now, their models suggest this is what's going to happen. And again, we're looking at this top of the aquifer as kind of the target level, and over the next 15 to 20 years, as they increase that pumpage by about 15 million gallons a day, that's what they're predicting is going to happen. We've reviewed that model. We don't totally agree with some of the results. Unfortunately, our model isn't to the point where we can substantiate it or deny it totally. We're in the process of trying to add that overlying geology to put that detail in the model. A lot of that funding is actually coming from Illinois American. So they are interested in determining that answer as well. Another way of looking at it is with a graph like this, which is basically very similar to that graph I showed you before with the head versus pumpage. And all we're showing here is that we're going to get to that top of the aquifer level in another 15 to 30 years. If Champaign-Urbana keeps growing like it is, the question is, okay, what do we do after 2040? Or maybe it's 2030. I'm not going to answer that. I've got some quick cartoons, and then we can kind of bring this to a close. Here we have a low-capacity well. This would be very similar to a farm well. And then a high-capacity well here, which would be similar to the city wells or an industrial well or an ethanol plant or whatever you want to call it. And we're going to pump this well, and it pumps a little bit of water, and it makes a little cone of depression. And here's where the pump is sitting. Now, remember, this aquifer system is under pressure, so it's pushing water levels up in the well above the top of the aquifer. So you don't have to put your pump down in the aquifer. You just need to get it below where the water level sits. If you put it way down at the bottom, then your pump has to lift. Well, actually, it only has to lift that same amount, but it's adding expense in terms of column pipe and what have you to the pumping expense. Okay, now what happens if we turn on the big well? We get a bigger cone of depression created, and that can influence or will influence the water level in this well. And if it pulls the water level down below the pump intake, that guy's out of water. But his well's not dry. It's just that his pump is sitting too high. So the solution then is to lower the pump, and then he can pump water again. So that's a very simple situation where we have this well interference impact using the Mahomet Aquifer and a small user. Okay, let's look at a different situation. Here's a situation that we know exists out there, and in fact we're using it to some advantage to help us find some of these windows where the shallow aquifer, this Glasford aquifer, is connected to the deeper aquifer system, the Mahomet. And we've got this little window where the two are connected. In other words, that glacial work has caused that overlying sand to intersect or lay directly on top of the Mahomet. And we know this occurs. We've done some testing out just below Allerton Park where we've seen this connection. Now, one of the things that's interesting about that is that the water level in those two aquifer systems has to be the same where they're joined. So the red line depicting the pressure surface in this aquifer and the blue line depicting the pressure surface in this aquifer have to be together at this spot. If they weren't, boy, we'd have some weird metaphysical thing going on. Some kind of waterfall, I guess, would be going on there, okay? So one of the things that we're using is by going out in the field and measuring wells out there that are completed in one aquifer or the other, A lot of times this head difference is going to be 50 feet or more, maybe 100 feet in some cases. But as we see those elevations come close together, then we have some indication that these aquifers are coming, that they're talking to one another. Okay? And that tells us something. That's an area of that maybe recharge or enhanced recharge is going on. So now what happens when we pump this little well up above? We get a little cone of depression. Not much happens. Now we pump the bigger well. We get a bigger cone of depression. And again, the upper aquifer, the pressure surface in there, has to equilibrate with that. We see a stronger downward flow into that deeper aquifer. And in some cases, that upper portion of the shallow aquifer can be drained. And we actually are seeing that in the shallow aquifer out here. And the question then becomes, if we continue pumping and we completely drain that Glasford aquifer, we probably won't stay on that straight line curve. Because now our source water, that shallower aquifer, doesn't have any water in it anymore. So knowing how that's occurring, where that's occurring, is really important. So we can lower this guy's pump and he can get water again. The last little cartoon, this goes back to the situation I was describing earlier, where we have the Sangamon River as currently, and under natural conditions, is the discharge point for water, at least from the shallower aquifer system. But what happens when we start pumping the deep aquifer? We can cause heads to fall below the bottom of the river. We will affect the heads in the shallower aquifer, and we can actually pull water out of the Sangamon River itself. Now, we discovered this situation because of the Decatur well field. They were operating 2 wells very close to the river to enhance their water down at the reservoir. But what was going on was they're pulling water out of the aquifer, but it's pulling water out of the river. So when they put water back in the river, they're not really gaining that much. They're recycling the water. So George and some others pointed this out with some modeling work, and they have basically abandoned those wells. Now, they still have other wells that they use, but they're not next to the river. Okay. I mentioned the model before. We've kind of gone through this a little bit. George is modeling the aquifer. Here's some model output. I showed you that map earlier that showed the measured heads. Here's some modeled output. You can see that we're kind of coming close. But I think George and I would agree that the way that's modeled on the eastern side is kind of a fiction, because we haven't really incorporated that third dimension, that overlying geology yet. Would you agree, George?
Yeah.
You will, won't you? Now, here's the other thing I wanted to point out. You saw earlier that cone of depression in the Mahomet Aquifer. Here's the cone of depression as reflected in that Glasford aquifer, that overlying aquifer. So it is influencing water levels in the shallower aquifer. And we're doing a lot of work, Bill and a lot of people from the Geological Survey. We've been installing new observation wells all across the aquifer throughout the county here. Champaign's sitting right here. So we're adding wells to look at this, and we're doing this. We're also nesting those wells. So we have a well at one location that's completed in the Mahomet, and a well that's also completed in the Glasford above it. So we can monitor both aquifers at the same time, see how they're reacting. I threw this just into this presentation for shock value. Here's model predicted drawdown at the current pumping rate. You can see the cone of depression, and you can see how far that extends. Miles. That's the nature of these confined systems, is that pressure wave, that pressure effect goes out a long, long ways. A similar well pumping water at a similar rate over here probably wouldn't go it wouldn't go beyond a township. I think we estimate recharge rates to the aquifer in this area is what, less than 1/10 of an inch?
1.5.
Okay, 1.5?
No,
half an inch versus 18 inches. So it's a couple orders of magnitude difference. Again, keep hitting you with that picture. So a lot of questions are coming up about the impact of these ethanol plants. Overall, I don't think they're going to have a real big impact on the aquifer. Most of these are probably going to be pumping on the order of 1 to 2 million gallons a day. Looked at across the aquifer, that's not a lot of water. What the concern I have is the local impact. If you add a 2 million gallon a day pumpage to the model scenario that Illinois American has, that's going to draw that timeline closer. So it's water that's being used for ethanol production rather than drinking water for Champaign. Or in some of the cases like up here, we're talking about maybe cessation of flowing wells or impacts on local wells like I described earlier. Now, I would be remiss to end this discussion without talking about some of the current planning efforts. The governor, back in 2006, put out his executive order 2006-01. There's copies of it on the table here. I think many of you might have picked that up. It sets up a planning process, and 2 pilot areas were picked for Illinois. One, northeastern Illinois, Chicago and Chicago metropolitan area. The second area is the Mahomet Aquifer. Well, it's kind of the greater Mahomet Aquifer area, but it's 15 counties across east central Illinois. And what we're tasked with in that process is to try and look at not just groundwater, not just the Mahomet Aquifer, but all water resources, including the Sangamon River especially, and seeing how the availability of water in this area meets future demands. And so what's going on right now is several water demand scenarios are being assembled that will project water demand out to 2050. For the groundwater part, we're going to use that demand scenario in our model to look at the impacts of that removal of water on the Mahomet. And then we can start comparing water demand versus impact. And it gives us a pretty long planning horizon to look at. So there are some really interesting and exciting things going on right now that are going to be completed in the next year to 2 years that will tell us a lot about sustainability of the aquifer, or at least sustainability in terms of contemplated use. I talked about the hydrologic cycle earlier. It also provides a great framework for planning and management, because we're talking about the interrelationship of all these sources of water. You take one from one place, you're impacting water in another place. So removal of groundwater has impacts on surface water. Drought has impacts on both. Climate change has impacts on both. So we can look at those impacts, and that's what we will be doing. Now, the issue of sustainability, when I started out the talk, we talked about these value judgments, or judgments that go beyond just the engineering of my model output. Here's kind of a depiction of a variety of things that go into these decisions. One of the things, obviously, that's probably most controlling over anything is economics. How expensive is it going to be? What's the best way to do it? So, how are we going to manage our water supplies in the future? Well, we could continue with the business as usual scenario, and that pulls into discussion what's called the rule of reasonable use, and I'll talk about that in a second. That's the current groundwater law. It's the current water law of Illinois. Or we can go to some other system, permitting system, some type of more regulatory management system. However that's decided, there's a lot of pieces to that water supply puzzle, and here's just a few. You know, we need to know what the availability of the water is, what are the demands going to be, what are the impacts of those withdrawals, what are the impacts on surface water, how does water quality fit into that, conservation and reuse, which could certainly play a big part. Then we start talking about drought and climate change. And then how far out should we put our planning horizon? It's one thing to set a planning horizon of 2020. It's another to put it out at 2050. And I think we all recognize that 2050 brings with it a lot of uncertainty. There's really no way we can predict how much water we're going to need 40 years from now. But we can put together a variety of planning or scenarios and say, okay, if we assume X, Y, and Z, this is what it's going to look like. If we assume A, B, and C, this is what it's going to look like, and just see what happens. And that's what we're about. Now, in Illinois, this rule of reasonable use is one that basically means groundwater is not owned by anyone. You have the right to use it, but you don't own it. And so you hear a lot of stories and a lot of people out there, they own land out there, and they said, I don't want you using my water. Well, it's not their water. And so, frankly, the way it's set up is if I have a high-capacity well, I can pump that in as much as I want to, and if I impact you, well, that's just too bad. As long as I'm using that for some beneficial, reasonable use, if I'm producing ethanol, I can go ahead and do that. Now, as an affected landowner, if I have the little well, I have the right to sue and say, you impacted my water supply, I want you to make me whole again. And what that does is basically just takes it to the court system, and a judge or a jury or however it's decided, they decide. That's not necessarily the most efficient way to do it. And the outcome is up in the air. Nobody really knows what the outcome might be. And, in fact, in some cases, it could impact a beneficial use of the aquifer because somebody's saying, well, you're going to impact my well, therefore we can't fully develop the aquifer. Now, in practice, what we've seen, especially like with the ethanol plant out here, is the proponents, well, and in fact, the Illinois American is in the same situation. They have said, they will deepen the wells of anybody they affect. And that's probably the better way. You're not dragging it through the court system. You're working with the landowner to help them and assure that they'll have a continuous water supply. Now, the people that live out there might not necessarily agree. They're happy with what they've got, but that's basically the way it is. So, prior to this executive order, we really didn't have a process for planning at all. So this is really the first time that the state has taken this step towards long-range water supply planning. Now, a committee has been formed for East Central Illinois. It's composed of 12 people. They are stakeholders, that is to say, each one of these 12 members represents some interest group, and they are meeting on a monthly basis to try and put together this kind of management scheme. We are basically going to be supplying them the science, the technical background. They have hired a consultant to look at providing us the demand scenarios. And the intent is that by June of 2009, there's going to be a document that says, here's kind of what the future for the Mahomet looks like. Here is a variety of scenarios. Here's a variety of impacts. Here's what we think ought to be done. I think all of you that are really interested and want to be engaged in that process, you could go to our website and learn more about it. You can get in touch with the committee members and certainly enter the discourse. We have several committee members here today. So, it's an ongoing process, and I think, it's kind of going to have an exciting future. And with that, I'll end my discussion. I'd be happy to take questions. Yeah, Bill.
One question on the chart that you showed about water being drawn down from various municipalities. You didn't indicate how much was going down to Kaskaskia to Tuscola.
That's not, being treated here, but we are by far the largest user. So probably 20 million gallons of the 23 is probably being used here. Yeah.
Given that and increasing usage, all of that water being pumped out and going outside of the confines of the aquifer, I assume it's not feasible, at least economically yet, or will it ever be, to try to do something to recharge within the aquifer rather than having it go elsewhere?
Well, I would say it's probably at least not yet economically viable. I'm not sure that we have a need for that at this point. There are other portions of the aquifer that we could tap into. And I guess one opinion that I have is that if we're capturing that wastewater, why try to put it back in the ground and then pump it out again? If it's reusable, let's reuse it, treat it, and use it directly. So, I mean, it's just taking water use.
If you put it out on the surface somewhere, and then it basically gets treated by the natural action.
Yeah. Well, you'd have to put it in the right spot. Like what we're saying, you can't just put it out there and hope it gets into the aquifer in any relative soon time. You'd have to find a spot where it's connected, and frankly, at this point, I don't necessarily see a need for that. I don't know how we're going to increase that 1.5 inch per year recharge rate. Now, the only thing I could say is that if we do, in fact, start, a problem with the Glasford, and we're seeing some dewatering of that now. if that were to completely dry up, that may impact recharge to the deeper aquifer, and that might be something that we want to try and keep a head on, so to speak. So it's possible. Ralph?
I have a constituent inquiry which I answered off the horseback. They want to know whether a future gen of Effingham would have any effect whatsoever on the aquifer.
Well, it's not at Effingham, it's going to be at Mattoon, but no. Jim?
Today you talked about sustainability really in terms of volume. Are there any implications of these various management strategies that affect other areas of sustainability, such as altering to chemistry of the water, increasing the likelihood of surface water centering the aquifer?
Well, certainly that's in the mix. And some of those things we can't totally investigate in the time we have and with the budget we have. We know, for example, that the Mahomet and the Glasford has, in some areas, pretty high arsenic concentrations, naturally occurring arsenic. So how increased withdrawals might impact that, we can't really predict. At this point, I don't know that there really is an impact other than to say you don't want to put a new well in where there's high arsenic. But that, in fact, could control, say, maybe where some future development does occur. Another aspect, I talked about this interconnection to surface water. You know, if we start pulling a lot of water out, will we impact flows on the Vermilion? And that's a designated scenic river. You know, that's probably not a good thing. We know, we have some interconnection to the Sangamon. We haven't really seen any flow impact on that yet, but that's always a potential. Yeah.
What is the impact on the Glasford when you get that reverse flow when you're sucking water from the Sangamon into the Glasford?
You would probably, if you had a well very close to the river, you would probably see some water quality changes. But you'd have to probably be pretty close to the river. And remember, that only occurs during certain periods, not constantly. And so once it goes... Well, we haven't...
I realize the potential for...
Yeah. And of course, once we go back to a more natural condition, that flow would be reversed and go back to the river. So it's kind of a flux situation. You wouldn't see any impact once you got...
What we see is actually more dilute, better quality groundwater. the nitrate and other things in the surface water get used up, get consumed in the stream bed. So the water quality actually tends to be much better than where groundwater can be coming up from bedrock or somewhere else.
Let's take one more question, and then I think we've got to wrap up with more.
Yeah.
What happens to the permeability of these layers? If you're going to pull water from the sand, would that affect the permeability of the rocks, or is it a reverse flow in the air?
We don't know of any permeability change. Most of these deposits, frankly, are over-compacted. So draining them probably isn't going to cause a subsidence impact, at least as best we know.
Okay. Well, let's...
Oh!